The goal of this tutorial in 3 chapters is to provide useful information on how to read maxon motor specification sheets in the maxon catalog. Essentially, a motor is an energy converter, transforming electrical power, it is current I and applied voltage U, into mechanical power given a speed N and torque M. We have a closer look at this power transformation and its limitations. However, we start with considering the requirements imposed on the motor by the application task. Essentially, for a given application, the motor is required to run at certain speeds and deliver a certain amount of torque. In our standard diagram with motor speed as a function of torque, this can be represented as points of operation. For example, a constant operation at a given torque and speed. There might be an operation point at higher speed but at lower torque, or maintaining a position against some external force at 0 speed, or accelerating a mass inertia, which usually needs the highest torque. In the first chapter we treat the motor speed and torque limitation. It's about finding the right motor type and size to cover all the operation points. We start with looking at motor speed. We need a motor with a speed limit that is high enough to cover all operating points. The maximum permissible speed corresponds to the upper limit of the operating range diagram. In our case here, the operation point with the highest speed cannot be covered. We would need a different motor with a higher speed limit. However, if this high-speed operation is not needed, the original motor is good enough. The speed limit of maxon motors can be found in line 23 in the mechanical data section or in the diagram. Next, we look at torque. All the operation points can be condensed and summed up in a few key values: the average, root mean square, load torque, and the extreme operation point, usually at the end of the acceleration where the maximum torque and maximum speed occurs, and the duration of the maximum torque, it is the acceleration time. We need a motor that can produce the necessary torques. A continuous torque corresponding to the average load and the torque for short-term operation, that we will cover later. The steady-state torque capability of the motor is represented as the continuous operating range limit in the diagram. It corresponds to the nominal torque in line 5 of the motor data. A suitable motor for our application needs a nominal torque that is larger than the root mean square average torque required by the load. The origin of the nominal torque comes from the maximum winding temperature limit. Up to this torque, the motor can be loaded continuously without overheating the winding. Higher torques are possible, but only for a limited amount of time. At the nominal torque, the maximum winding temperature is reached under standard conditions. If heat dissipation is better than standard, the continuous operating range extends towards higher torque values. This can be achieved, for example, by mounting the motor on a large heat-dissipating structure, for instance a metallic frame or a cooling fin. Heat dissipation is also improved at low ambient temperature or by forced airflow. It's quite easy to enhance the continuous torque by about 25%. However, be aware that reduced heat dissipation can have the opposite effect. For example, the motor is derated at higher ambient temperatures. It is possible to overload the motor for a short period of time. This is indicated by the short-term operating range. In reality, it expands to higher torque levels than shown by the white area in the standard diagram. How long an overload situation may last depends on the amount of torque and the motor type. Essentially, the limitation comes from the winding temperature, more precisely, how fast the winding heats up. The natural time scale is, therefore, the thermal time constant of the winding. It can be found in line 19 of the motor specification. Typically, the thermal time constant amounts to a few seconds for small motors, up to half a minute for larger motors. In our case, it's about 11 seconds. How to read the diagram and the time scale at the bottom. At torques up to about twice the nominal torque, the overload can be quite long, 20 seconds for small motors, up to several minutes for larger motors. At an overload of 3 times the nominal torque, the duration, however, is already shorter than this thermal time constant. The load torque of the indicated operation point is about 2.5 times the nominal torque. As a rule, the maximum duration amounts to about just this thermal time constant. How does current come into play? In reality, it's the motor current and not the torque that heats up the winding. However, torque and current are related, the relation being very simple. There is a strict proportionality between the two, with the torque constant Km as the proportionality factor. For a given motor, current and torque are equivalent. So instead of a torque axis, we could have drawn a current axis. Accordingly, the current at the origin of the nominal torque is called nominal current, IN, and can be found in line 6 of the motor data. The torque constant is given in line 12. It gives the amount of torque in millinewton meters produced per 1 amp of motor current. Power supply and/or controller typically impose continuous and maximum current limitations. Since current equals torque, this results in torque limitations. As a consequence, the continuous and short-term operating ranges might be restricted. Load operation points that could easily be handled by the motor might not be achievable anymore due to the lack of sufficient current. The key messages to keep from Chapter 1. Motors have speed limits. They stem from consideration about bearing and brush life. Motor torque and current are equivalent, with the torque constant Km as proportionality constant. Motors have torque limits. The continuous torque limit is given by the nominal torque or nominal current. Motors can be overloaded for a limited time depending on the amount of torque. That's it. The end of Chapter 1. You can find Chapter 2 and 3 in separate video tutorials. They explain motor behavior and the properties of the winding series.